Hello, my name is Andrea Bragas. I am a professor at the University of Buenos Aires in Argentina. And today I will divide my talk in two parts. In the first part, I will give you some flavor of what we do in our group in Buenos Aires. And then in the second part, I will try to share with you some information I collected from my colleagues in Latin America to see what is the state and what we do nowadays in photonics research and development in Latin America. So let me first talk about the first, give you first the idea where my country is. It's in the very south, as you see there, very far from everywhere. But the country has many different natural beauties, as you can see, from high mountains, the highest mountain in the whole Andes mountains, colorful mountains, and you have whales, penguins, many things. What you can come and visit, you are very welcome to come. You're going to enjoy a lot this country. It's very nice. More or less in the middle of the country is Buenos Aires here, where my university is in the middle of the Pampas. It's a very rich part of the country too. And also, okay, here you can see our campus at the University of Buenos Aires. You see the city behind there. And the campus is a very nice place also to work. Again, you are very welcome to come. So let's start with a little bit about our work in nano-antennas. Here you can see more or less the different projects we are working on nowadays. In nano-antennas, mechanical nano-resonators. I will talk a bit about that later. Metal surfaces and also optical forces of magnetic origin, but I won't talk about that. Let's talk a little bit about nano-antennas. Nano-antennas, the word is inspired in this nano-antennas, the Professor Yagi is holding here, the radio frequency antenna, and the idea is that these devices, which are constructed in the nanoscale, are able to convert the propagating radiation, electromagnetic radiation, into very concentrated and enhanced energy in the near field, okay, and vice versa. So these antennas are on the order of the nanometer scale because are scaled with the wavelength of the light, okay. So one of the more representative things of these antennas are that you can find these hotspots, known as hotspots, where the energy is concentrated and enhanced. So, you can imagine that with that, you can do a lot of applications, a lot of things, and I will won't go into this in detail, but just, tell you about a couple of things. For instance, you can do nonlinear optics in the nanoscale. You can see that you can see that in the nanoscale you can apply the tricks as phase matching or things like that because you have very little matter, and so the idea of having these hotspots is very useful for generating nonlinear signals. In this case, we generated second harmonic signals in this world. We put these nano-antennas are a pentamer of gold discs, and in between the discs you have these hotspots, and in that work we managed to put a nonlinear material. In this case, it's this zinc oxide nanowire. We put it in one of the hotspots, and then in figure B here, when you take the second harmonic signal, this is the imaging of the second harmonic, you can see in these blue spots corresponds to the light coming out from the pentamers, but in the pentamer in the middle where the nonlinear material is, you collect much more light, okay? There is an enhancement of the light coming from that place, and you can do this in different wavelengths, as I show here, and with that you can reconstruct that is coming from the plasmonic resonance related with these with this structure. Okay, at that time we got the second harmonic efficiency, which is very low because we are in the nanoscale, but at that time was a record. Nowadays, people is doing much better than that. Another example I want to give you is that you can do that not only with plasmonic nanoantennas, but also with dielectric nanoantennas. And that has many advantages. One of that is that it's not generating so much heat as with the metallic and plasmonic antennas, but still you can get a very useful hotspots at high concentration of light. In this case, these are two discs made of silicon, and in the middle of that, the gap here is only 20 nanometers. It's very challenging from the point of view of the fabrication, and we published this paper in 2015. And it was a very nice paper. It was one of the first papers showing this in dielectric antennas, and we collect the light. I mean, we did Raman scattering. We put a polymer on top and do Raman scattering, and we collect the Raman scattering of some vibration of the polymer on top, and we show that we have enhancement in each one of the positions where the hotspot is, and okay, and show that this is comparable with plasmonic nanoantennas. Okay, so let's go into another function, let's say, or application of these nanoantennas, which are that you can convert that nanoantennas into mechanical nanoresonators. Indeed, when you come and illuminate this antenna with an optical pulse, where the pulse is shorter than the period of the normal mode of these nanoantennas, you can kick that and produce the vibration of these antennas at the frequencies of the normal modes of the antenna. In this case, this is a simulation of a nanorod that is vibrating in its extensional mode frequency. These frequencies are on the order of gigahertz and tens of gigahertz. So depending on the, of course, on the size. Okay, so the signal that you collect, because the way to see this movement now is to come with the second pulse, which is called the probe. And now your plasma resonance is moving at the rhythm of this movement. Okay, so if you are at a given frequency, a given wavelength with your probe, what you see with this movement is that your signal is going down and up, and then you collect a signal like this one, where you can see this is the differential transmission as a function of the probe delay, this probe delay that you came with, and then you see that these oscillations are the frequencies of the normal modes. In this case of the rod, you have two frequencies. The extensional mode, this is this lower frequency one, and then the breathing mode, which is this higher frequency. Okay, but that is not. I mean, I'm not going getting into details, but just let me tell you that as you imagine, you can use these tiny nanoresonators, mechanical nanoresonators as sensors. Now you can sense the mechanical properties of the material which is surrounding the nanoantenna. And then you can, for instance, as in this sketch is showing, you can measure the vibration of the nanoantenna before to cover the nanoantenna and after to cover it with the polymer films, for instance, or other materials. And collecting the shift of this frequency, because the frequency changes when you put this material, because the restoring force now is higher, the frequency is going to higher values, and then measuring that and comparing with simulations, you can simulate that, and comparing with simulations, you can collect the, for instance, Young modulus or shear modulus, here you have in this plot the frequency shift as you measure experimentally and the frequency shift that produces in the simulation. And then with the, for instance, the average value you can get from there, you can extract yours, the value. And this has at least two advantages. One is that these antennas can give you a very local measurement of the mechanical properties, because you can measure this in average, you can measure in different places and average the whole values, but also you can measure it individually and you can get a very local measurement. And the other advantage is that you can do that in the gigahertz regime, okay? This polymer or this film that you're measuring is moving the gigahertz, and there are not many methods that can give you the mechanical properties in the gigahertz regime, which is very, I mean, it's relevant for the functioning of devices nowadays. So the other thing that is very important for these nanoresonators is that they can couple to the underlying substrate and launch these surface waves, as in this simulation is showing. And then these waves have wavelengths in the order of few hundreds of nanometers. It is very useful, and you can, for instance, put another antennas in far from the place where you produce the antenna, and you can measure again the movement optically with the probe pulse. And with that, in this paper, we show that this is a surface acoustic wave. I'm not getting into details, but we managed to measure the speed of that wave and the amplitude, and with all that, we concluded that is a surface acoustic wave. And also you can manage the directionality. You can engineer new nano antenna in order to get a directionality in the surface acoustic wave. We show that also in this paper. And again, and also you can, for instance, focus the surface acoustic wave by fabricating some device as this one made of an arc of discs. Here again is how the energy, now acoustic energy, is concentrated in a very small place on the order of 100 nanometers in this case, okay? So with that, I just finished this part, and I want to thank my group, these four guys, especially, who are the people who did the work actually, and my collaborators, especially in this field, Stefan Meyer and Emiliano Cortez from LMU Munich, before in the PDL College. Okay, so let's go now the second part. How is the progress of the photonics in Latin America, let's say. Okay, first of all, I went to the IEEE webpage and saw the different photonic research centers they collect in the webpage, and I've seen only 20 centers in Latin America, let's say Mexico and South America, and Central America. And actually, I just by counting the information I collected, I count 60 institutions in only 8 countries. So there are many more institutions in Latin America. Of course, some of them are bigger and some of them are smaller, but there are many more institutions nowadays working in photonics. And I will give you some information I collected from these 8 countries, and especially from this is 8 in blue, and also some other countries are players in this landscape, as Venezuela, Peru, and Bolivia, but I don't have information right now. I'm sorry, but especially among these 8 countries, I will talk about Brazil, Mexico, and Argentina, which are the biggest countries doing research in photonics. So first, let me give you some information about the historical information. because after the laser born in 1960, there were a rapid development of the optics in Latin America countries, especially in Argentina. In 1964, I put these are snapshots of a movie. It's an institutional movie at the School of Science of my university. And they already showed different lasers functioning at that time in the 60s. And in this video is from 1964, and you can see a gas laser. I don't remember now which gas laser is working. And they show how they light a cigarette, and also how they drill a brick in that video. It's very funny, the big, but that show us how the at that time the development of the optics, let's say, we didn't talk about, you know, photonics at that time, so was high in Argentina. And also this is a picture I collected in the 1965, where they constructed the first helium neon laser in Latin America, in Argentina. Another player here is this guy, Sergio Porto, who came from the United States. And he was in Bell Labs and also at the University of Southern California in Los Angeles, and they wanted to create in Brazil an institution that he wanted to be the equivalent of Bell Labs in Latin America, in particular in Brazil. And he could do it because the University of Campinas at that time was new created and really had a huge development in photonics from there since then. So let me give you like a timeline of how the different Latin American countries start to organize after the 60s, after the birth of laser. So in the 40s, in 1948, the International Commission for Optics, ICO, started to work, and the countries in Latin America asked for joining, and you have here the dates. In 1972, Mexico joined the ICO, and Argentina in 81, Brazil in 84, Colombia 90, Cuba in 93, Venezuela 97, and Ecuador was the last, I guess, in 2015. And then under the umbrella of the ICO, they started to organize as territorial committees in each one of the countries and organize their own meetings. Were called Optilabs at the first, and this is the optics of laser, and also there were another meetings which were Ibero-America meetings. So it's Latin America plus Spain and Portugal, called REAO, that started in 92, and then they merged as a joint conference, REAO Optilabs, in 1998. And from 2012, the Optical Society of America, currently Optica, started another conference, a Latin America conference in photonics, which is called LAO. Okay, so here you have the different communications at the two conferences, REAO Optilabs and LAO. And you can see that is, you have the contributions of the different countries. Mexico has participation, the highest participation in both of them. And then Argentina, Brazil, and the others also have some, some participation. Let's say that the researchers, of course, want to participate in all the international conferences as well. So, and also there are student chapters in almost all the countries, from Optica, SPIE, and IEEE. And they organize also some workshops and conferences. Here, this slide was provided by Optica. These are the numbers from the last conference they organized, the LAOP, that was in Brazil this year. And here you can see that the contributions are much more than the half from Latin America and the others from the other countries. And here you have the distribution in terms of countries. So Brazil, Mexico, Colombia, and Peru have the higher number of contributions to that conference. Okay, so let's talk about the different countries, the 8 countries I mentioned before. First, Brazil. As I mentioned, Brazil started to work in photonics in the 70s, and really it has by far the highest development in photonics. They have more than 5,000 people involved in photonics, working in photonics, if you count researchers and students, and that is huge. It's a huge number. And most of the people is working in Sao Paulo area, actually. Here you have, this is the map of Brazil, and you can see how the numbers are distributed, and you can see that here, the red zone, which is the zone around Sao Paulo, is has the highest number of people here working in photonics. Also, they have a very well developed ecosystem of photonics, meaning that they also have companies, not only the academia working at research and development, but also they transfer the results to companies, and they have more than 300 companies working in photonics in Brazil. They are national companies, and also some others, 300 more, which are international companies working in Brazil. But they really have development in all the areas, especially in telecommunications, and also technology of information, medicine, and many others that are listed here in the left. Here you can see all the areas, photovoltaics, and the only maybe thing that they don't have much development is in defense and security. But you can see here the publications. These are called periodicals. Here the publications, the groups, the professionals, the people, and also patents and national companies. Okay, so that they really have, I mean, the photonics very well developed, and the ecosystem is working in Brazil. And I can say that maybe that is the only country in Latin America that has this possibility nowadays. Mexico is another interesting example. They also have a very well developed photonic system. Maybe they don't have that transfer to companies so developed. They have about 500 professionals working in photonics. They have these clean rooms, very important clean rooms in the country. And also there are 4 important centers. They are the acronyms there, where they give photonics undergraduate and graduate degrees. And they cover all these fields here: optical metrology, optical sensors, for what they have these clean rooms, research and engineering in solar energy, artificial intelligence, robotics, and so on and so forth, and nonlinear optics, many other things, and biophotonics. So more or less they cover all the things, but still I guess that they need more development in the thing that they have to transfer the knowledge to the industries. Okay. In Argentina, that we started very early because we developed the laser very early in the 60s. We don't have that development at all. There are more or less 300 professionals working in photonics, but many other related things, related research. We can add another 300 working in related areas, but specifically working in photonics, we can say that we are 300. Here is the country, and you can see that the centers are all over the place. And we do all this. I mean, mainly all the fields in photonics, but we definitely don't have any. We don't have development in terms of transfer to companies. The only, I mean, maybe exception is the satellite companies. We transfer. I mean, there are many groups working in machine processing, and we transfer that knowledge, and also professionals working in satellite industry companies. But as you see from the basic point of view, we cover more or less all the fields. Okay. Then I mean, there are the other countries with in terms of number of people working, and also development and research and development and transfer are smaller. As in Chile, Chile has a very interesting experience of building these Millennium Institutes. And in particular, there are almost 40 of these institutes in Chile, but in particular, they have one of, devoted to the optics and photonics. And there is this MIRO, Millennium Institute for Research in Optics, and they have more or less 20 seniors working on that. And also in other places of the country, they have another 20, let's say. And they work in quantum optics, optical networks, image processing. Image processing is a thing that all over Latin America is very well developed. And I think it's because you don't need much money to that, and we have really a lot of people very well developed in that. Okay. Ecuador also has some groups scattered all over the place, and they work in quantum optics, optical tweezers, plasmonic fiber optic communication, and sensing. Uruguay also has very nice work. I mean, 3 or 4 groups in Montevideo, in the capital city of Uruguay, and they work again in image processing, remote sensing, optoelectronics, and quantum optics and information. They are kind of pioneers in quantum optics and information. And also, I can mention Cuba. Cuba had very well, I mean, its highest splendor in the 80s. But since the 90s, the situation of the optics in Cuba has been severely punished by several factors. We know that the economy went down, but because, I mein, they entered in a crisis. And after the pandemic, they really lost almost everything. And many of his professionals are out of the country, sadly. So we don't know what is going to happen with that. And Colombia, I did not receive data, but if you want to see what is happening with Colombia, is very, very interesting also. It's growing in photonics. There are many, many groups, as this graph shows. And I took this graph from this paper here of it's a paper of this year. And you can, I mean, it's in Spanish, but you can translate it. And it's very interesting situation, because they are growing in these days in photonics in different fields. Okay, so and this is my last slide, and I want to thank a lot the people who give me some information about this thing of the photonics in Latin America, and in Brazil, Anderson Gomez and Gustavo Wiederker, and Mexico, Eugenio Méndez, Mayo Villagrán, en Argentina, Jorge Torgan, Gabriel Vilmes, en Ecuador, César Costa Vera, in Uruguay, Arturo Lezama, in Cuba, Luis Ponce, and in Chile, Carlos Saavedra. So thank all of these people for giving me the information, and I have this, and if you want to read about that, I have all the information that I can give you a more detailed, reading and things I have, and I can give you that too. Thank you for your attention.